In the last video, I was nearly back to the stage of being able to continue with teaching myself to hover my homemade helicopter. But my drive shaft started to fail. The failure was predicted by comments, so not a surprise. It could have worked with some changes, but I decided on a much better option instead. In this video, I'll make the new drive shaft, test it, and hopefully continue teaching myself to hover. There were quite a few comments in the last video pointing out that the machine is hovering tail heavy. It certainly looks tail heavy. There is more to this than meets the eye. Let's start by carrying out a static hang test. The machine is very close to level. I don't fully understand what's going on, but here are some thoughts. Firstly, the field slopes away from the gate, not by much, but it's enough to alter the perspective. The tail vanes. As yaw is controlled with tilting vanes using the rotor downwash, this will push downward on the tail when the vanes are deflected. I don't know how much of an effect this will have, but it will have some. If the tail vanes aren't significantly pushing down on the tail, then there is another explanation. We notice that every time the machine lifts off, it starts fairly level, then the back drops and it sinks back down to the ground. What needs to happen when the back drops is an increase in power and a forward cyclic correction. I'm not sure if I'm carrying out this correction, possibly because I'm not brave enough right now. If we look back at the hover in April 23, there is no sign of this back dropping repeated cycle, but there is if we go back further to September 22. In the April 23 hover I was pretty confident and quite relaxed. I know in the September 22 hover I was nervous and not comfortable at all. I'm told in moments of great stress humans adopt the fetal position. This means inadvertently pulling back on the cyclic, or at least a reluctancy to push forward. Also bear in mind I was pushing significantly forward when the drive shaft broke in 23. The wind had picked up and was pushing me backwards at this point in the day. The relationship between pushing forward and something bad happening might have prevented me applying the necessary correction. A new plan is to try and make myself push forward, but also actually move forward. It's been suggested that moving forward helps to learn because you don't have the unsettling backward motion and there is some help with yaw stability. This is only very slow edging forward motion, not forward flight. That's the plan anyway, and I can't wait to try it, but first I need to make the new drive shaft. There is one other explanation to this rearward drop, and that's rotor flatback. A gust of wind will cause this, pushing the rotor backwards, and the drop in height above the ground is due to the disturbance of the ground cushion. When the rotor is moved around, it reduces the efficiency of ground effect. With my hovering so close to the ground where ground effect is so strong, this disturbance is very noticeable. Getting higher off the ground makes things easier, but that takes some bravery, particularly when I've got little confidence in the reliability of the machine at the moment. Building the drive shaft then. The first thing I had to do was make a sleeve to slide the ball spline nuts off the shaft. Then I needed to cut a section of shaft. We can see the depth of the case hardening here. I cannot cut the hardened casing with a tungsten carbide turning tool, so I mounted my angle grinder in the lathe to be able to cut and face the section. Now I have a small section, I can use my profile projector to measure the size of the ball grooves. They measure 3.6mm diameter. I then drilled those holes into a test female part and bored the centre hole to fit the shaft. I inserted 3.6mm diameter pins into the holes, securing the shaft. Now I can test the strength of the design applying at maximum engine torque of 55 pounds-feet. To apply torque, I tapped a hole in the shaft M12 and inserted an 8.8 grade M12 bolt. M12 8.8 grade bolts only have a maximum torque setting of 59 pounds-feet, so I need a higher strength bolt to test this to double engine torque. If you want to know what the 8.8 stands for, it's 800 MPa, 80% yield. 10.9 is 1000 MPa, 90% yield, and so on. MPa is megapascals, which I always convert to PSI because that means something to me. I'm happy with the test, so can proceed with making the top universal joint yoke, and that starts with cutting some material on my shaper. I made a hacksaw attachment to use my shaper as a saw. I just had to move the auto feed to the vertical slideway. It has a built-in clutch which slips when the feed rate is too high for the sawing speed. Next, I'm turning this squarey bit into a roundy bit. To drill the 3.6mm holes, the part needs to go into the mill, and I really like this centre finder. I've also drilled and tapped some M3 holes for a retaining washer. Back in the lathe again, and I've bored the centre hole. Now into the dividing head so I can start milling the yoke. One thing that takes a lot of time is clocking everything in as accurately as possible. Each division on the clock is 1/100th of a millimetre or 10 microns. The carbide end mill running as fast as the mill spindle can go is tearing through the material in no time. I know they cost more than HSS, but boy, they are time saver. I drilled and bored the cross hole and removed the unnecessary material. 6082T6 machines nicely. A big thank you to JLCMC for supplying me with the wonderful ball spline, sponsoring the video and also providing even more parts I needed. Everything ordered arrives quickly, the quality is very good at a very affordable price. I wanted some carbide end mills for speeding up the process of making the universal joint yoke. They sell a variety of end mills at sizes from 1mm to 20mm diameter. These are my new favourite cutters. They have a great selection of circlips, internal and external, and a large range of sizes. I needed some circlips to retain the ball spline nuts. I also needed a 10.9 grade M12 bolt to be able to test the universal joint yoke at twice engine torque. JLCMC have a nice selection of bolts to choose from, including some speciality bolts not so easy to find. They also provide transmission components, aluminium enclosures and extrusions, pneumatic system parts and much more. Check out the description for a link to the website and coupons. Thanks again to JLCMC for the great parts and sponsoring this video. The last time I made this, I put the circlip groove in with this tool on the milling machine. So it was in the milling machine on a rotary table, so it spin round in this direction, and I cut the groove like that. In that video, someone suggested, why don't I make a bit in the lathe to be able to put this in here, and then I can spin it in this direction and use a lathe tool. Now all I can say is, what a stupid idea. Pathetic, actually. I need to turn down a section of the ball spline shaft, and the only way to do that is to use my grinder again to remove the hardened case. I don't want it getting too hot, so need to cool it between passes. Once the case is removed, I can go back to using the turning tool. Next I need to broach an internal keyway into the aluminium tube, and for that I'm using my shaper. First I need to make a keyway cutter on my tool grinder. The shaper is great for doing keyways. It does a really nice job and doesn't take long. You can make any size keyway you want and it's accurate. The tricky part was getting the two keyways exactly opposite each other, which I didn't manage. I had to remove 0.2 of a millimeter off one of the keys. I'll have to think of a better way next time. The last bit is to make the bottom flange. The 5mm radius at the bottom of this turn section was made using coordinates. The lathe digital readout doesn't have a radius function, but the mill readout does. I just used that to work out the correct coordinates. Drill the holes, remove the unnecessary material, and that's it. Ta-da! Really happy with that. That is so nice. The top is held on by a circlip in there, and I hammered pins into here, and there's a retaining washer to stop them coming out. The nuts in here I had to hammer in as well. It's just a really nice thing. The centrality of this cross hole to the center of the shaft is 0.02 of a millimeter off center. Really happy with that. Obviously I've got two keyways in there to try and keep these two nuts balanced. I don't think there's any more to say. Oh yeah, there is. Let's try it. So here we have the 3 drive shafts, attempt number 1, number 2, and finally number 3. Number 1, I used constant velocity joints. They were tripod CV joints. The problem is the shaft in the center was free to float, which wasn't ideal, and also the CV boots couldn't take the RPM, so lubrication was a problem. The only reason it failed is because I used this rubber donut here, and I stopped this bottom joint sort of flapping about by a very small shaft that went into the clutch, and that was my mistake. I shouldn't have done that. Otherwise it could have worked. We know a lot about number 2. This design worked apart from the design of bearing I chose. I chose a different type of bearing. That could have worked, but I'm really happy with number 3. There is no backlash. It's just, I think, the solution. The first one weighs 3.8 kilograms, the second 2.7 kilograms, and the third is 2.9 kilograms. I've got 2 concerns with the new shaft. One, it needs to spin at 5,500 RPM without any issues. I don't know if it will cause an issue. Hopefully not. The second is there's a bit too much friction in the sliding, and that can be solved either with running it in, or I could go down a ball size, say 5 microns smaller on the ball bearings, and that would free it up perfectly. But let's see if it will run in first. As the new shaft is quite a bit smaller than the old one, the shroud is a little big, but I won't have any problems with contacting. Well, that is nice. It actually frees up in its movement with RPM. Increase the RPM, freer it gets. I was kind of hoping for that scenario. Obviously, when there's torque applied, that could make some difference. But from my tests on the bench, just torque testing on the bench, it didn't really change in how much friction it took to slide in and out. So really good, and the balance looks perfect. I know I haven't got a dynamic balancer, but just by comparing the last drive shaft to this one is definitely smooth. Shall we put the blades on? You know that exhaust cracking issue I thought I'd solved? Well, there's a crack. I know my welding isn't very good in aluminium, but it hasn't actually broken on the weld. It's next to it. Weld it up for now, but still the plan to make new exhausts out of steel. Right then, today the wind is going down the field, which is unusual. We can sort of see, well, I probably can't tell, but the place where it is now is fairly level. It does slope away slightly, it then gets steeper about there, and then it levels out down there more. But it's no better down there than it is up here. And pulling the helicopter from down there is quite a bit of work. I could do with some sort of electric gizmo to help pull the machine. That would be a nice little build. Right, today, well, start off with, I just want to test that drive shaft and spin the blades up, check things are okay to start with, and then we'll go from there. Well, that felt good. Felt like I was higher than I actually was. Not confident, I would say, but heading in the right direction. One thing I did notice was the ignition switch, or master switch, has melted. Well, it's got too hot anyway. Bit surprised why that is. I can't see a reason for it. I can change the switch. We'll see if it does it again, I suppose. Obviously check the amperage it's rated for, but I would have taken that into consideration. I know the draw is about 18 amps. New switch is installed. Had a look at the old one, and 25 amps is what it was rated for. Wow. What I'm trying to do is be a bit braver with the controls. Obviously there is a fine line between too much movement or being too brave and not brave enough. Everything feels quite good on the drive shaft at the moment. No concerns there. Well, I've had a good look round it and I can't find anything to fix, which is bizarre. Very unnerving. Well, the plan now is I want to just take it down the field and then just see if I can come up towards the gate. I don't know if it'll be possible, but it'll be fun to try. Here is the issue. I'm not going high enough to safely go forward, because I know if I touch that front skid while I'm going forward, it's likely to tip over forwards, blades hit the ground, everything gets smashed to bits. I'm not brave enough to go higher. I just can't make myself do it. So going forward doesn't feel particularly safe at the moment. I need to be able to get higher before then. Cool. Someone just started up their lawnmower. How inconsiderate. Some people.
Here's the problem. The wind is picking up and it's quite gusty. You get a sudden gust of wind, you go up, and it also pushes you in the direction where the wind's coming from. So if I had a gust there from the side, it pushed the rotor to the side, I had to react quite quickly to bring it back. And of course it goes up as well. It's not conducive to learning how to hover. I'm not going to make any progress unless the wind calms down a bit. So there's not much point in continuing with it like this. That wind gust to the side definitely unnerved me. It reminded me of the video, the dodgy moment video. That was exactly the same. Gust of wind to the side, pushed the rotor to the side. I didn't counteract it with enough force, and it ended up being a landing sideways, which wasn't much fun. And the machines with cyclic and collective pitch aren't going to experience the same force as I do, because this takes more force in general to move it around. And if that gust of wind has to be counteracted with quite a lot of force, not a lot of movement, but quite a lot of force, then I don't think I can control that the way things are. If we look at the Nolan brothers, and they achieved a lot with a tilt rotor type design, but they had hydraulic cylinders. I don't think they were pump assisted, but they might have been. I just wonder if they did that to try and solve this force problem. I mentioned before about reducing the ratio so that it's easier to move left and right. That might make a difference. Someone suggested just bringing this stick up higher so you've got more leverage. Yeah, I've done that before actually. I had it up much higher, and I reduced it back down again because I was hovering okay, but only in real calm conditions. The April 23 video where I'm hovering really nicely, it's about a foot off the ground, look, very happy. Those were perfect conditions. And even later on in the day, as the wind picked up, it got gusty, and it got twice as hard to try and control it. On the plus side, I'm very happy with the drive shaft. The overrun bearings, which I haven't shown, are working fine. The teeter bolt is fine, that modification, it's all good. The belt isn't ratcheting, no adjustments needed there. So a lot of problems have been solved. It's just where to go from here. In perfect conditions, I think it is going to be possible to hover this and move forward. I think that is achievable. But I think it does give me an insight into the kind of problems people like Igor Sikorsky would have come across in the development process.